Hello and welcome to the exciting conclusion of our lesson on 2-2, polynomial functions of a higher degree. And in this video, we're going to be doing a lot of graphing, and then we will end with this something called the intermediate value theorem. So here, let's see how all this stuff we've been learning ties into making a decent sketch. Sketch the graph of f of x equals 3x to the fourth minus 4x cubed. We got 4 steps. 1, apply the leading coefficient test. So I know this is a positive x to the fourth. So I know my graph is going to go up to the left and up to the right. So over here on my graph, just real light, I'm going to draw a little up arrow to the right, little up arrow to the left. That's my end behavior. I'm going to start here maybe heading down, and then some stuff might happen. I know at the end I'm going to be over here heading back up. So 1, leading coefficient test. Step 2, find the real zeros. So we're going to set our function equal to 0. 3x to the fourth minus 4x cubed equals 0. Well, we can't factor a 3 or a 4 out of both sides, both of these numbers, so the 3 and the 4 are going to stay. But we can factor out the x cubed. And that will leave us a 3x minus 4 equal to 0. So here is a 0. If we set the first term x cubed equal to 0, x cubed equals 0. So x is 0 is one of our real zeros. I'm going to put a dot on the graph now, and that's going to be right at the origin. And because it's an odd exponent, it's odd multiplicity, that means we're going to cross at that point. So keep in mind, we're going to cross the x-axis at the origin. We've got another factor, though. This one is odd multiplicity, quantity to the first. So we're going to cross at this, we're also going to cross at this one. Odd exponents we cross. So if I set 3x minus 4 equal to 0, I'm going to add 4, 3x equals 4, and then divide by 3. X equals 4/3. So we've got another 0 at about 1 1/3. So if I come over to my graph here, I'll make this 1 and this 2. And we're going to cross the x-axis at about 1 1/3. So here. So there's our zeros. Step 2 was find the zeros. Now it does say plot a few additional points. Let's see if we can find some easy ones in there. Like plugging in a 1 or a -1 is usually pretty easy. Here's +1 on our x-axis. If we plug in +1, that'll be 3 times 1 to the fourth minus 4 times 1 to the third. 1 to the fourth and 1 to the third are just 1, so that's just 3 minus 4, or -1. So if we go over to 1, we go down to -1. And let's put a -1 in the function and see what comes out. Oops. So we're going to have 3 times -1 to the fourth minus 4 times -1 cubed. Because this is an odd exponent, we'll multiply this 4 times and that negative will disappear. So this turns into a +1, just a 3. Here, a -1 to the third power, this negative is going to escape and hit that and turn into a plus. So that'll be plus a 4 times 1 is 4. 3 plus 4 is 7. So if we go over to -1, we're going to be way up high. And that is, that's our end behavior. We're going to be heading up pretty quick. So let's sort of start drawing our graph. The last step from here, we're heading up. I'll come down across the graph. We know we hit the x-axis at 0 and we cross. And we know we go through this point, and then we're going to cross again at 1 1/3. And then that's perfect because we got to meet up with this end behavior arrow going up. So parabolic in shape, open and up. Again, this is just a sketch. There could be more twists and turns in there. Let me bring up the book's graph and it'll most likely be better. So there they get the end behavior, they get the x-intercepts. Yeah, so there, it sort of flattens out. My graph should have been a little more like this, flattening out, and then it come down. But, this is just a sketch. Just a sketch. We're just having fun here. Technology. In that last example, example 4, in that example we used an algebraic approach to describe the graph. A graphing utility can complement this approach. Remember to find a viewing window that shows all the significant features of the graph. For instance, the viewing window here in the top graph illustrates all of the significant features, every little bump and our highs and lows, and we can see what the end behavior is up to. Viewing window B does not. B is just zoomed in too far. On our TI-89 calculators, I believe that's the F2 menu, is our zoom. See here, this bottom one, we're zoomed in, and they cut off this bottom part of the graph here. And that's an interesting part. We want to see that. We might want to figure out where that minimum value is. So you can always adjust your window. A polynomial function is in standard form when its terms appear in descending order of exponents from left to right. To avoid making a mistake when applying the leading coefficient test, write the polynomial function in standard form first, if necessary. So let me make this a little bigger. There's our function. We've got negative 9/2 x plus 6x squared minus 2x cubed. So there they were trying to trick us, and they put the higher powers near the end, but they're not going to fool us. We'll just rewrite it. And let's rewrite it. Well, yeah, let's just take that step. Negative 2x cubed plus 6x squared minus 9/2 x. And let's set it equal to 0. We know we're going to need that in a minute. Okay, now we've got the leading coefficient here. It's a negative and it's odd. If it's negative and odd, we're going to head up to the left and we will fall to the right. So there's our end behavior. That's taken care of. Find the real zeros. So let's factor out. We're definitely going to factor out an x. And to get rid of the fraction, I'm going to multiply out a 1/2, or factor out a 1/2. Let's get rid of that negative, because I like my leading term to be positive. And we'll pull out an x. And I'm going to have to get rid of this end behavior error. I'll just hide it up here. There we go. So let's see, we factored out a negative, so that's a positive term now. And because we factored out a 1/2, that number is going to double to a 4. We factored out an x, so it's x squared. This sign's going to switch because we factored out a negative. How many halves are in 6? 6 divided by 1/2, invert and multiply. There's 12 of them in there. And now that x is down 1 power there. And then since we factored out the negative, this is going to change to a positive. We factored out the 1/2, so there's 9 left there. 9. Ooh, oh, factoring out that 1/2 was key. Because look what we have now. Now this, we could spend some time doing the ACB method or a little trial and error, but I notice my leading term, 4 is a perfect square, x squared is a perfect square, 9 is a perfect square. We're subtracting in the middle and adding at the end, so we're going to, both our terms will have minuses and they'll multiply to a positive. My suspicion is this is a perfect square trinomial. So let's see if that would work. So if my assumption is right, this is going to be a quantity squared. The square root of the first thing would be a 2x. Bring down the minus. Square root of 9 is 3. It's all down. Does the middle term work? The middle term should be this times 2. 2x times 3 is 6x, and if you double it, you get 12. So that did work. We found our factorization, and I forgot this is equal to 0. Because we are doing a second step here, find the zeros of the function. So I'll slide this out of the way. All we got to do is set our factors equal to 0. And notice right off the bat, here's an odd one. This is where we're going to cross the x-axis. If we set negative 1/2 x equal to 0, divide by negative 1/2, you get x equals 0. And here we are, again, we are going to cross. So maybe what I'll do, I'm going to, instead of a dot, I'm going to put a little, let me move this over. I'm going to put an x on that value, and that will signify to me that we're going to cross there. If it's a dot, we bounce. So here we're going to hit the x-axis and we're going to cross. And if we set this in the parenthesis equal to 0, let me get a little more room to write over here. Set 2x minus 3 equal to 0. We're going to add 3 2x equals 3. Divide both sides by 2, x equals 3 halves. 3 halves is 1 1/2. So if I mark my x-axis, here's 1, here's 2. I'm going to use a dot because we are going to bounce at this one. We will not cross. Uneven multiplicity means we bounce. And it says also plot a few additional points. Let's see, what would be an easy one to do? Now let's just put a 1 in there, f of 1. So that would be negative 9 1/2 times 1, that's negative 4.5. Oops, negative 4.5. Plug in a 1, square it, you get a 1 plus 6. So that takes us to what? Positive 1.5. 6 minus 4 1/2 is 1.5, and then we subtract 2 times 1 cubed, that would just be 2. 1 half minus 2, negative 1 half. So if we go over to 1, we're down here about negative a half. Remember, we bounce here at that one. Okay, this does make really good sense here. Yeah, that's enough points. Remember our end behavior, I had to erase it, was sort of up this way to the left. So if we're up this way and we start heading down, we are going to cross at the origin, and then we go through this point, and we have to get met up with this downward arrow here for the end behavior, and no problem, because here we're not going to cross, we're going to bounce due to the even multiplicity, and it'll come down like that. Whoa. Let's see if the book's picture is better than mine. I would suspect that it is. So there's the end behavior, up left, fall to the right, and we've got our x-intercepts, and they plot the points. Yeah, not too bad. Well, actually, what they did, okay, I see what they did. They used a half in there, it looks like. They might have used a half to get that the lowest point there, that little valley bottom. All right. This one, just a couple here to graph on your own. This will be a nice, easy one. And this one here, when we get to that, I would factor out a negative 1/4. You know, you could make this 3 halves into a 6/4 and factor out a negative 1/4. And I suspect it'll be a lot like our last example. Pause the video, try the problems, fire it back up to see if you got them right. All right, we are in descending order, so we can get our leading coefficient test out of the way. It's positive odd exponent, so that is going to be up to the right. It's going to fall to the left. Let's set this equal to 0 and factor out what we can. Looks like we can factor out a 2x squared, and that would leave an x minus 3 equal to 0. If we set this first factor equal to 0, that's supposed to be a squared. Oh, and notice that squared, it's even multiplicity. So here, this when we solve this one, here we're going to bounce off the x-axis, divide by 2 and take the square root, x equals 0. So at 0, we're going to bounce, and I used a dot to represent that. The next factor, x minus 3, that's first power, odd multiplicity. So when we set this equal to 0, we're going to get a cross here. So add 3 at x equals 3, 1, 2, 3. We are going to cross the x-axis. I used a little x last time. All right, an easy point. Let's maybe try a 1 and a negative 1. If we put 1 in there, 2 times 1 to the third, minus 6 times 1 squared is 1. So that's just 2 minus 6, or negative 4. So if we go over to 1, we would go down 1, 2, 3, down to negative 4. And that makes sense. Looks like we're going to complete the graph this way. And let's see if we put a negative 1 in. Whoa. A negative 1 in there. That'll be 2 times negative 1 cubed. So that negative will escape and make that a negative 2. And then we'll have minus 6 times negative 1 squared. That square will eat up the negative, so that's negative 2 minus 6, or negative 8. So if we went over to negative 1, we're going to be way down here at negative 8 already, way off what I have on my graph. So I'll switch to green ink. We're down here, working our way to the right, so we're coming up. We're going to hit the origin, but we do not cross. We bounce because of the even multiplicity. We found this point down here, and we're going to turn back up because we've got a cross at 3, and that meets us right up with our end behavior arrow, and we're away. Beautiful, beautiful sketch. Okay. It's even multiplicity or even exponent there, and it's negative. So the end behavior here will be down, down. And I told you to factor out a negative 1/4. And we could also take out an x squared there. So let's see what's left. We factored out the negative and the 1/4, so that's out. An x squared out of there leaves us an x squared. Here the sign will change. We factored out a negative, and that 3/2 is 6/4. We factored out a 1/4, so there'll be 6 left there. It's like we pulled the denominator out and the numerator fell down. And now then we're going to have a positive there, sign change. Factored out the denominator 4, so the 9 is left all alone. The x squared was factored out entirely. Ooh, this is looking good. What's in those parentheses needs factored. And it's x squared minus 6x plus 9. Perfect squares at the beginning and the end. Let's try to make that x minus 3 quantity squared. And check our middle term. This times this is 3x, and if we double that, we get the 6x in the middle. Middle term checks out. Our factorization is good. Let's set this first one equal to 0. So that's an easy one. Just set it equal to 0, divide by a negative 1/4, and square root. So we get x is 0. Note again the even multiplicity, so we are going to bounce at the origin. Bounce at the origin. This next factor is also even multiplicity, so here we're also going to bounce off the x-axis. Set x minus 3 equal to 0, and you get x is positive 3. 1, 2, 3. We're going to bounce again. I guess we could do another point or so. Well, yeah, let's do another point. I just didn't want to maybe deal with those fractions, but let's make that a 6/4 again, because it's easy to plug in a 1. If I plug a positive 1 in there, I'm going to get negative 1/4 times 1 is negative 1/4. Plus this x cubed will just turn into a 1, so we've got 6/4, and then minus, that'll also turn into a 1, 9/4. Common denominator's all there, so then it's be negative 1 plus 6 is 5. 5 minus 9 is negative 4. Ooh, and that worked out nice. Divide that, you get negative 1. So over 1 down to negative 1, and that makes sense. Well, let's see. We're down here at our left end. Our arrow's heading down, and we're heading up, and we know where we're going to meet up with the origin, but we're going to bounce. We bounce off the origin. We know we go through this point, and then we're headed back up at 3, and then we bounce again. And that works because we got to meet up with this arrow for our right end behavior. Good times with graphs. The last topic here, it's a little calculus tie-in. You'll see this in calc. The intermediate value theorem. It says here the intermediate value theorem apply. Oh, well, let me do it like this. Let's say here, I've got a point down here, x1, y1. And our function also is going to take us to this point, x2, y2. The theorem states that we have to be a continuous polynomial. And I can pick any value in between the endpoints. I'll just call this, I'll just put a question mark there. I can pick any number in between. And the intermediate value theorem says this value has to come from a value in between x sub 1 and x sub 2. Think about it this way. If I switch to blue ink and start at this dot, can I get to this other dot without ever crossing that red dotted line? Well, if I head up this way, oh, I got to cross it to get to the other dot. Maybe I sneak over this way and I cross it again to get to the other dot. It's impossible to get from this dot to the other dot without crossing that red line. Wherever we cross, this is the x value that made it happen. And that's all this intermediate value theorem says. We have to take on every value between x sub 1 and x sub 2. And this theorem says we're going to take on every value between y sub 1 and y sub 2. So again, we could pick this value anywhere in here, make that red dotted line. We're going to have to cross it to get to the other dot. So here the IVT implies that these points are 2 points on the graph of our polynomial function. And this is key here. F of A and F of B are not the same height. You know, F of A is down here, F of B is up here. It could be reversed. The point is they're not the same on the y-axis. There's some gap in between them. Then for any number D in between there, somewhere in between, here they got their red dotted line in the middle, D between f of A and f of B, there is some number C down here between A and B on the x-axis, such that when we put C into the function, out pops the D. F of C is equal to D. Remember that D just represents our height over here on the y-axis. So here in the box is the official intermediate value theorem. Let A and B be real numbers such that A is less than B. If f is a polynomial function such that f of A is not equal to f of B, then somewhere in that interval between A and B, f will take on every value between f of A and f of B. So here A is less than B. They're saying A is over here, B is over here. Function f of A is not the same as f of B. So maybe my f of A is here. I'll put f of B up higher, f of B. As long as they're not the same on the y-axis, this theorem will apply. Then somewhere in between A and B, or back to, it says, then in the interval between A and B, somewhere in between here, our function will take on every value between the outputs. One application of this intermediate value theorem is to help you locate real zeros of a polynomial. If there exists a value, some x value, at which the polynomial function is negative, and then another x value for which it goes positive, or if you reverse that, then the function has a zero in between those two values. Where is this? So here it says, for example, the function x cubed plus x plus 1. If we want to find the zeros, we might try to factor it. It does not factor nicely. But if we start testing some numbers, if we put a negative 2 in there, out pops a negative value. When we put in a negative 1, out pops a positive value. So let's look at this down on the graph. Let me go back to red ink. When x is negative 2, we get this value down here at negative 3. And then we put in the next whole number, negative 1, and we're up here at positive 1. So if I want to get from the red dot to the blue dot, I have to cross the x-axis. And if we're crossing the x-axis, then that is a zero of our polynomial. Notice here it's between negative 1 and negative 2. It's probably some third root or square root of something. It's not going to be a nice clean number. And here, what we've done, we haven't exactly located it, but at least we know where it is. We know its neighborhood. It's somewhere in between negative 1 and negative 2. And then, you know, we could continue that reasoning. We could try to take between negative 1 and negative 2 and chop that up into 10 intervals. Negative 1.1, negative 1.2, negative 1.3, all the way to negative 2. Maybe put them in a calculator and see again where we switch from positive to negative values. So here in example 6, it says use this IVT theorem to approximate the real zeros of this function. We're not going to be able to factor it and set it equal to 0, so we're going to have to try something else. And what we might just start with is trying a little plug and chug, a little trial and error. So let's see. Let's try negative 1. Oops. F of negative 1 would be negative 1 to the third that's a 3, minus negative 1 squared plus 1. So this, the negative would escape because of the even or odd exponent, negative 1. We would square this one away to positive, and then it's a minus 1, and then plus another 1. So when we put in negative 1, out pops negative 1. So f of negative 1 is equal to negative 1. So we could plot that point. Negative 1 would be right here. Let's try f of 0. That's an easy one to do. 0 cubed is 0, minus 0 squared is 0. So that's 0, and then at plus 1, positive. Jackpot. Look what happened. We put in two adjacent numbers, negative 1 and 0. And then we've got out a positive number and a negative number. What lives in between positive and negative? 0 is in there somewhere. So the intermediate value theorem says somewhere in between, well, let me plot this on the graph here, 0, 1, so it'd be up here. So again, think about this logically. Can we get from the black dot to the blue dot without crossing the x-axis? It's impossible. Somewhere in there has to be an x-intercept. And you know, maybe this theorem's not going to help us find it, but we could say by the IVT, by the intermediate value theorem, somewhere between negative 1 and 0, there is a value such that f of c, f of that value, is going to equal 0. And again, we know it's between negative 1 and 0 because we have to cross the x-axis to get to the next point. And that's it. You know, we can't find the exact value, but we know it exists. In calculus, they would call this an existence theorem. And there's the book graph, a little bit better than mine. And you know, here between negative 1 and 0, we do have an x-intercept. So a little summary. Well, no, that's explained. It's not really a summary. This one, it would be nicer if we had a tiein. Why don't you save this one? We'll do this one at the start of class because this is a great one for the TI-89 calculator. And even put in your notes here, we are going to use this table feature. You might not remember the table feature on the calculator. You're going to want to use the green diamond button. There's a green diamond on there that's blue, and I should have changed to green ink. Green diamond F1 is the y editor, and you'll type in the function y equals, and you'll type in x cubed minus 3x squared minus 2. And then we want to make sure we can input values on the table. So here I'll switch to green ink. So there it is. That's a little better. Green diamond F4 will take you to table set. Table set. And what we want to have that set to is ask. If you scroll down where you'll see a little a menu, ask or auto, automatic or ask. We don't want automatic. If yours is in auto, switch it over to ask and make sure you hit enter twice. Once to choose, once to save. So after we have green diamond F4, and then we'll hit green diamond F5, and that will take us to a table. And then we can start punching in numbers, +1, +2, +3, you know, -1, -2, -3, and we'll start looking from when we change from negative numbers to positive or positive to negative. All right, so I will see you in class when we will work on this problem. The homework for this section, just check WebAssign or the Teams page.